Hi, welcome to Modern Optimization Methods. Today we will introduce Chapter 6, Semi-smooth Newton's method. This is the outline of this chapter. We will start with the definition of semi-smoothness, then we introduce the semi-smooth Newton's method. After that, we will discuss the support vector machine problem, and we will apply the semi-smooth Newton's method to that SVM problem. Finally, we will present some numerical results by exploring the sparsity of the problem. Now we start with the first part, the semi-smoothness. Semi-smoothness is originally proposed by Mifflin, and before that, we need some preparations about definitions. For example, we assume that this phi from m-dimensional space to l-dimensional space to be a locally ellipsis continuous function. And according to Redmacher's theorem, phi is differentiable everywhere. Based on this assumption of phi, let's define the sets where phi is differentiable as d phi. Okay, so d phi represents for those points at which phi is differentiable. Okay, so we collect all the differentiable points and put them in d phi. Let phi prime denote the Jacobian of phi at any differentiable points x in d phi. These are some preliminary notations that we will use later. So based on the notations here, we make further definitions. We introduce the Bolligand subdifferentiable at x is defined by the accumulation point of phi prime at xk, where this xk is actually converges to x, and xk is a differentiable point of phi. Then the phi prime of xk will converge to an accumulation point. Such point we denote it as v. So all the collections of this point v we defined as the B Bolligand subdifferentiable of phi. We use the partial b phi at x to denote this B Bolligand differentiable. Okay? So let's take a look at a simple example. The small phi is actually a maximum of 0 and x. Then from this definition, we can see that the point that phi is differentiable is actually infinity to 0 and 0 to positive infinity. In other words, except 0, all the other points in R is continuously differentiable, all right? And at 0, this is the main focus we will think about. And for other points that x is not 0, we can easily calculate the d prime, okay, the Jacobian. So for x greater than 0, it is 1, and if x is smaller than 0, it is 0. Therefore, at 0, this point, we can calculate the Bolligand subdifferentiable according to the definition here, and we simply take the negative sequence and the positive sequence tending to 0 to take the limit of the phi prime, and then we can get that the Bolligand subdifferentiable at 0 is either 0 or 1. It's a collection of 0 and 1. Now, let's introduce the convex hull of a set. A convex hull of a set is defined by all the convex combinations of the points in this set. Okay, so recall that we have introduced the convex combinations in Chapter 1, which means that all the coefficient of xi is between 0 and 1, and all the sum of the coefficients will be 1. In that case, this result will be called the convex combinations of the points x1 to xn. So for a set X, we take all the elements or any elements from A and we take the possible convex combinations, then the resulting set will denote as the convex hull of A. So coming back to our simple example, if we got A as 0 or 1, the two sets of points, and we take the convex combination, then the resulting set will be interval between 0 and 1. Okay, so this is the convex combination. Now after that, we are ready to give the Clark's generalized Jacobian. The Clark's generalized Jacobian at a point X is actually a convex hull of the B-polygon subdifferentiable. In other words, the Clark's generalized Jacobian, which is denoted as partial phi at point X, is the convex hull of the polygon set. Now, coming back to our example, the generalized gradient for max function is actually given as following. It depends on the choices of x. If x is 0, then it is actually the definition, as we mentioned, is the combination between 0 and 1. Therefore, it is a value of v, where this v is between 0 and 1. So it is a multi-value function at this moment. If t is not 0, then it is actually differentiable. Therefore, the convex hull or the Clark's generalized Jacobian coincides with the Jacobian of phi at x. Therefore, if t is greater than 0, then the Clark's generalized gradient is 1. If t is smaller than 0, then it is 0. Okay? So this is a simple example to demonstrate what is the Clark's generalized Jacobian. Now, this figure actually shows us that what or how the generalized Jacobian works for the max function. Okay, so this is a curve for the max 0t, this function, and we can see that this curve is differentiable everywhere except 0. So in other words, except t equals 0, all the other points, they have unique Clark's generalized Jacobian. And if t is 0, then we have to calculate the generalized Jacobian by first calculating the B-polygon subdifferentiable, then take the convex hull. Okay? So the polygon subdifferentiable is the limit point of the gradient, right? So we take a sequence from the left-hand side to approaching to 0, and the phi prime will be 0. And another sequence from right-hand side tending to 0, with the phi prime is 1. So the B subdifferentiable is 0 or 1, 2 points, right? Then we take a convex hull to get 0 and 1, this interval. Now, having given the generalized Jacobian matrix, then we are ready to give the definition for semi-smoothness. So the concept of semi-smoothness was introduced by Mifflin, firstly for functionals, and then it was extended to vector-valued function by Qi and Sun. Now, the definition for semi-smoothness has two conditions. First one is that phi is directional differentiable. Another one is that for any matrix V between or inside of the generalized Jacobian of phi at x plus h, this point, we have this expansion, okay? So if we take a detailed look at this expansion, it basically says that the function value of phi at x plus h minus the function value of phi at x, and then minus v multiplied by h is a high order of the length of h. It seems that this formula is a bit similar to the Taylor's expansion. In fact, as we compare this equation with Taylor's expansion, the difference we can find that it lies in this v. Okay, so in Taylor's expansion, if we do Taylor's expansion of this function phi at x, then the v here should be the subdifferentiable or the Jacobian of phi at x. However, for the definition of semi-smoothness, such phi actually comes from the subdifferential or generalized Jacobian of phi at x plus h. Okay, so it's at this point rather than x. Okay, so in other words, it actually means that if this h comes from the left-hand side, then this formula basically means that I do expansion along the left-hand side, then I can get the high-order approximation. Okay, so the v actually depends on the coming direction h or the changing direction h. All right, so if the second formula holds together with the first one, then the phi is said to be semi-smooth. Now, we also have a very special definition called gamma order semi-smooth. It means that if phi is semi-smooth and further the following equation holds. This equation is similar to the semi-smoothness definition. However, the difference lies in the order of h. Okay? If we take a look at the order of h, we can see that it means that the left-hand side can be written as the same order of phi in the order of 1 plus gamma. Okay? Here gamma is a positive number. So this is called gamma order semi-smoothness. Until here, we have defined two semi-smoothness. Okay, one is the general semi-smooth. The second is called gamma order semi-smooth. We have a very special definition for the gamma order semi-smoothness. That is, if the gamma value is 1, okay, then we have the following equations reduces to the expansion of phi at x plus h is the same order of the norm of h, the square norm of h. Okay? So in this case, we call the semi-smoothness strongly semi-smooth. All right, so this is a very special case for gamma order semi-smoothness, which is called strongly semi-smooth. We will talk about strongly semi-smooth later when we apply our semi-smooth Newton's method to support vector machine. Now, again, we demonstrate this figure to show the semi-smoothness. Okay? Actually, for the Marx function, it is strongly semi-smooth. So as we can see that the strongly semi-smooth basically says if we do a sort of linear expansion along the coming direction h, we will get high order approximation. And compared to the Marx function is basically piecewise linear function. Okay? So in other words, if we come from the left-hand side approaching 0, it is actually a straight line. So by this expansion, we can actually calculate that this term is exactly 0 because you got only linear term, right? So this linear term is fully represented in this part, and this term will be 0. In other words, this max function is a strongly semi-smooth function. If we do a little bit extension, any piecewise linear function, they are all strongly semi-smooth. Okay, so this is a result. And for other results about semi-smoothness functions, we can actually see that any composition of semi-smooth functions will be semi-smooth. And any strongly semi-smooth functions, their compositions will also be strongly semi-smooth. Okay? So this is some existing results about semi-smoothness. In other words, if we try to verify whether a function is semi-smooth, one way is by definition, another way is by some existing properties like this. Okay? Now, let's make a brief summary about this part. In this part, we mainly introduce the definition of semi-smoothness. So to reach the definition of semi-smoothness, we first introduce the Bolligand subdifferential, then the convex hull, and the Clark's generalized Jacobian, and finally we reach the semi-smoothness. Okay? So we stop here and see you next time.